concept. Okay, so if there's no questions, we'll move on to the next section, which deals with, what is a zero? So we're going to define something called a zero. Simple definition. Is zero of a function is set of all the x values, the set of all the x values that satisfy the equation f of x equal to 0. That's what we mean by the zeros. It turns our function into a zero value. So let's take a look at some of these. So for example, I have my f of x equal to x squared minus x minus 12. And I tell you that, x equal to 4 and x equal to a negative 3, those two x values are zeros. Well, what might we do? We could verify that. So at this stage, all I want you to do is just to verify something is a zero. So meaning I compute f at 4. So I start with that, which is equal to 4 squared minus 4 minus 12. Well, 4 squared, as we can see, is equal to 16. Minus 4 minus 12 is, in fact, 0. So x equal to 4 is a 0 of that parabola. Then we could check f of negative 3. Everyone do that. Plug in f of negative 3 and make sure you do find that to be a 0. There's a common mistake that many people make with that. Just verify that for a second. Do it, see if you do indeed get that. So hopefully everyone does get it. Let me show you it works. You have to use parentheses, especially if you do it on a calculator, because the calculator will give you the wrong answer. Okay. A negative 3 squared is a positive 9. Subtracting a negative 3 becomes plus 3. Subtracting 12, 9 plus 3 is 12, minus 12 is 0. So it works. Now what about x equal to 1? Is that a 0? So if I tried, is x equal to 1 a 0? Well, it's not, because when I plug in 1, I get f of 1 is equal to 1 squared minus 1 minus 12. Well, I just get negative 12, which is not 0, so it's not a 0. So it's not in the set, and it doesn't satisfy that condition. Okay, so that's some real numbers. Let's take a look at some other ones as well. So this is relatively easy, this section. This is just an introduction to what a 0 is. It's going to get much more complicated, but at least we start out in a simple fashion. So, say for example, I give you this function. The second example, f of x equal to x squared plus 4. And test to see which are zeros. So find which are zeros. So x is equal to, say, negative 2, 2i, and a negative 2i, and a positive 1. Test those out, and are any of those zeros. So try that. Try that and see if you can find if any of those are zeros of that quadratic there. Sometimes it gets a little more complicated. And hopefully you do see 2i and negative 2i are both zeros. Does anyone want to see that? Anyone want to see where I found that those two satisfy f of x equal to 0? Is everyone comfortable with that? Okay, let's plug it in. Let's verify that that doesn't work. So f of negative 2 is equal to a negative 2 squared plus 4. Well, negative 2 squared is a positive 4. 4 plus 4 is 8, which is not 0, so that's not a 0. Doesn't satisfy that definition. Well, let's put in f of 2 times I. That's equal to 2 times I squared plus 4. Well, that is equal to 2 squared times I squared plus 4. 2 squared is 4. I squared, remember, that's negative 1 plus 4. So that's negative 4 plus 4, 0, so it works. Let's plug in negative 2i. So f of negative 2i is I take entire negative 2i and square that, and then add 4. That's going to be a negative 2 squared times I squared plus 4. Well, negative 2 squared is 4. I squared is again negative 1 plus 4. I get the same thing, negative 4 plus 4, I get 0. And 1, as you can see, 1 squared is 1 plus 4 is 5, so that does not work. So you should be able to test, is something a 0 of a function? Is it an x value that will make that function value 0? So you can see it can be a real number, it can be an imaginary number. There's another case, it could be an imaginary number. So let me give you a couple of these to try and see how well you can do. Some of them are more elaborate when you're dealing with radicals. So you should be getting, your algebra skills should be well enough to handle these. If not, then this is an opportunity to practice some of your algebra skills to do this. So here's a thing to try. So f of x equal to x squared plus 6x plus 2. And my x I want you to try, there's a couple of x's I want you to try, is we'll try, try this, an integer, a decimal value. You can see does it work or not, as well as this, minus 3 plus the square root of 7. Try those and see if either one of those are a 0 or not. And then another one over here I want you to try as well. Yeah, when you're working on that one, I'll make up a problem here quickly. On my own. Well, the algebra gets a little bit tricky over here. both of these, those are the numbers that work. So you can see a 0 can be very complicated. Decimals can sometimes be used to approximate it, but that one does not work out too well. I've got my... Does anyone want to see how I verify that that one doesn't work, but that one does work? And number 1. Okay, so let's kind of plug everything in and see what we get. We'll try the first one. It's relatively easy. So I put in f at negative 5.6. That's a negative 5.6 squared plus 6 times negative 5.6 plus 2. Plugging that in, plugging that into your calculator, you should get 31.36. And then minus, when I plug that in, I get 33.6. And then I add to that my plus 2. And I should get 0.76. Found a little typo in the book as I'm looking at 0.76, which is not 0. Hopefully everything kind of works out so the number's okay. That does not work. Not a 0. So let's move on to the other one and see if we can do that one. That one we can do a little more precisely. So I have my f at minus 3 plus the square root of 7. Okay, it gets a little more complicated now. So what do? I plug this in, so I get my negative 3 plus the square root of 7 quantity squared plus 6 times negative 3 plus the square root of 7 plus 2. Well, we need to do a little bit of algebra over here. So let me just do this up top. Well, in fact, let me do it down over here. I'll actually kind of do it this way over here. So I'm going to take and write that as negative 3 plus the square root of 7 times negative 3 plus the square root of 7. So negative 3 times negative 3 is a positive 9. And notice what I have. A negative 3 square roots of 7, another negative 3 square roots of 7 gives me negative 6 square roots of 7. Okay? Then I get the square root of 7 times the square root of 7 gives me 7. I can add the 9 and the 7 together, and this just gives me 16 minus 6 square roots of 7. Okay, so I multiplied that out. Okay, coming over here, I can multiply the 6 times the negative 3, so I get, I'm distributing that, negative 18 plus 6 square roots of 7. Plus the 2 that I have over here. Well, I can see right away they cancel out. 16 subtracting 18 gives me negative 2. Plus 2 gives me 0. So that works. That is a 0 of that function. Very complicated form of it. So the point being that zeros, the zeros can take very elaborate form. Just Colin.
When you put the negative 3 plus square root of 7 into the calculator, it comes out as 4 minus 4i. Is that because it's the calculator?
Oh, you did the square root. You have to do square, not the square root.
No.
Or you put a negative under the radical. You got to be careful what you did. If you plug it into a calculator, it will give you, if I square that, I can go to my online calculator. Well, it will never come out to an imaginary number. It'll come out to this number here, 16 minus 6 square roots of 7, whatever that is. It's some sort of a decimal number. Square root of 7 is... It will come out to be a positive value. If you got an I, you must have hit square root. You might have hit the button. If you look at on your calculator, see if it gave you a square root. Because you may have hit the second function button instead of the squaring function button. Because that's what you have to be worried about. Because negative 3 plus the square root of 7, the square root of 7 is less than, 3 in magnitude, so that's a negative number, but when you square it, it becomes a positive. You probably took the square root. That's the only thing I can imagine. Don't rely so much on your calculators. Can you practice this algebra? These are weights, little algebra weights that you need to practice lifting so you can get better at it. Too much reliance on a calculator means you're relying on a device to do all your work for you. So when it comes to the heavy lifting, where you have to do this and then some, you're not ready. You can't even lift the lighter dumbbells, and now you're asked, bench press 150, 180, 200 pounds or whatever. But this is the algebra that you should be able to do at this level. Now, interestingly enough, if I put a minus square root of 7 here, we'll talk about that. That would also be a 0, but right now we don't know that. Okay. Does anyone want to see problem 2? How I got that solution. Okay, let's plug that in and see what we get as well. Again, practice the algebra. This is so important. I can't stress enough because I have 6 students, Cal 1, Cal 2, Cal 3, and I call differential equations Cal 4, even though it's been modified over the years to be co-equal to Cal 3, but not quite. Most of the students, a lot of them still have problems in the algebra. Okay, let's plug in the first one. This is my f of x. Sorry, I didn't write that. So if I come over here, let's do it on this side. Put in f of -1. Let's see, -1 squared minus 2 times -1 plus 2 gives me 1 plus 2 plus 2, which is 5, which is definitely not 0. Not a root. It is not a 0 of that function. Now let's take a look at this one now. Now I'm going to look at f of -1 plus I. Oh, maybe it's not that. Maybe it is 1 plus I. Yeah, it should be 1. That should be a positive one. I'm thinking through my head over here, kind of working on it. That's why you may have gotten it messed up. Yeah, it should be a positive one now, as I'm looking at it. I just made it up at the last minute. Yep. Should be 1 plus I. That's my mistake. Okay, let's check that out. -1 plus I won't work, but 1 plus I will. I'll show you the -1 won't work, and we'll show you this one does. I'll show both. Okay, let's plug that in. So I'm going to do 1 plus I squared minus 2 times 1 plus I plus 2. Well, let's square that out. 1 plus I times 1 plus I. So we just did that calculations with complex numbers. So what do I get? I get 1 plus, I plus another I, and then an I squared. Well, I squared, remember, is -1. -1. So that becomes canceled out, and I plus I just gives me 2I. This whole thing just gives me 2 times I. Let's distribute that. -2 times 1 is -2. -2 times I is -2I plus 2. And see what happens. Plus 2I, minus 2I, -2, plus 2 gives me 0. Now if you have that -1 in there instead, it would not cancel out. Let me show you that. So if I did put in -1 plus I, then I would have gotten my f of -1 plus I would give me -1 plus I squared minus 2 times -1 plus I plus 2. This is going to give me a -2I over here. So if I kind of, multiply that out, I'll show you again. So if I distribute -1, +1, I get 1. And then over here, I'm going to get a -I and another -I, -2I. I squared gives me a -1, so that cancels out to just give me a -2I. minus, okay, -1, -2 times -1 is a +2. -2 times I is -2I plus 2. So I actually get 2 and 2, I get 4 minus 4I, which definitely does not equal 0. So if I had -1 plus I as a choice, I would reject it. It is not a solution. So this is why we had you doing some of the arithmetic in the earlier sections. You may have to do some arithmetic with complex numbers, and this is where it comes into play. So it kind of enlightens us that our zeros can be simple real numbers, they can be integers, they can be fractions, they can be radicals, they can be pure imaginary, they can be complex numbers, they can be a whole host of different numbers. And a lot of times people like to approximate them with decimals, and that's good. But you also need to understand how they work in their exact value, because their exact values are important. Okay, so that's an important aspect of the definition. What we're going to want to do is find those zeros. That's going to be the crux of what we're going to do for the next section. Here I gave you those zeros to check. Can I find them on my own without being given them? And that's going to be the focus of our next few classes. How do we find them, and how do we know what type they are? You know, some of them are integers, some are different types, and that's going to be the focus, you know. How do we determine if a function has a zero and if it does, how do we find them? That question, this simple question, turns out it's really answered by something called the fundamental theorem of algebra. And that's our next section in 5.4. So the answer to this is something called the part answer. It's not so much how to find it. It tells you what you need to do, and then we're going to develop the techniques for finding it. But this is all about the fundamental theorem of algebra. It's actually a fundamental theorem of arithmetic, is that any number can be factored into its prime factors. Okay, now there are several versions of this. There's a very high-level one, which is not very useful, but many books use it, and it doesn't give as much useful information. I'll give you the version. It's a simply stated, that's why people like it, but I like the more practical version that we can use in a calculus class to help us determine what those zeros are and find them. So there's several versions. Here's version 1. Very simply stated, it says any complex polynomial function. Now, our functions here are going to be the algebraic ones, and it's essentially we're just going to deal with polynomials. We'll look at zeros of other functions later on when we consider transcendental type functions and analysis. But any complex polynomial function has at least one complex zero. Well, why don't I like this? Well, this is any complex polynomial function. We don't really see them. This is this is an example of a complex polynomial function. Maybe you have, 3 minus 2i times x squared plus, 2 minus the square root of 7 times x plus, I over 16 is equal to, that's my function. We very rarely see, it's complex because I have a complex number. And it also has radicals over here too. And I, throughout my career in, science and engineering, I very, very rarely, I've never seen any with complex coefficients. On a rare occasion, you'll see some, linear ones, but that's not so bad with radicals in there. But most of the time, all these coefficients are integers. So this version applies to anything you can draw up here. That applies to anything. So it is more general, but anytime you generalize something, it becomes less useful. So I prefer the different version. Now, a lot of the books will go by this, and they'll live by that, and they'll give you answers in the back, and I'm not a fan. So now we're not going to prove this. This is a very difficult theorem to prove, and version 2 is also difficult to prove. In the textbook, I put a link where it's a simple proof. It's not too bad, but I don't do a lot of the proofs at this level because most of you are not math majors, so there's not a lot to be gained from the proof. If a proof is something that gives you certain insight, I will do it. But here it doesn't really give you that necessary insight. But what I want to do is address these questions more. Using this version, it's not the best way to do it. So there is another version where we limit the type of polynomial functions. We're not going to deal with complex polynomial functions. We're going to deal with real polynomial functions, with real coefficients. And even with real coefficients, we're also going to further simplify it. So this is the version that we're going to deal with, and it gives us a roadmap on determining the types of zeros and kind of giving us information on how to find them. So this is version 2 of that. And simply states the following of the fundamental theorem of algebra, of FPA. Not arithmetic, but this time algebra. So in this case over here, an nth degree polynomial function with real coefficient, real number coefficient, so no i's and stuff in there. So with real coefficients, we'll have n not necessarily unique. It could have a repeated zero. It could be, 2 it goes and it actually repeats in terms of the number n. So we'll have n, not necessarily unique. Real or complex zeros. So what does that mean? Say I have a 4th degree polynomial. I know at the outset I'm looking for 4 zeros. Now they could be, real, complex, but there's 4 of them. They could be repeated. Meaning maybe I only have 1 unique zero. For example, let's take a look at a simple 4th degree polynomial. F of x is equal to x minus 1 to the 4th power. Well, what's the zero to that? Very easily, x is equal to 1. That's the only zero. The only number that will make it 0. So it's kind of like repeated 4 times. It's not a unique zero, but there are n zeros, meaning I can write this in factored form. X minus 1, x minus 1, x minus 1, x minus 1. So each of those is a 0. So I have 0, x equal to 1 is a repeated root. It's repeated 4 times. Okay. This is good, but it's not enough. I'm using, real coefficients. I want to further classify that or restrict it further, I guess you would say. So here is the further restrictions. And it says if the zeros are complex, so say I do have complex zeros, say the zeros are complex, then they must occur in conjugate pairs. Must occur in conjugate pairs. So meaning if 3 plus I is a 0, that implies that 3 minus I also must be a 0. Now, why is that? The reason being for that is I get real coefficients. If that were not the case, I could get complex coefficients. Because when you multiply them, the zeros, they come in conjugate pairs. You multiply this times that, it turns into a real number. So all the coefficients end up being real. So that's one if. And then we want to restrict it further. So instead of real coefficients, meaning including the radicals, say if the coefficients are rational numbers. So if the coefficients are rational numbers, it could be integers or even fractions or this crazy thing, but no radicals in the coefficients. So there are no radicals in the coefficients. Then the zeros must occur in radical conjugate pairs. Zeros must occur in radical conjugate pairs. So both of these are going to help us. So what does that mean? Meaning, say I have one of my zeros. Say that I had that 0 that I just put in there, minus 3 plus the square root of 7. That's a 0. I'm given that. This tells me, as long as I don't have square roots as my coefficients, this tells me my other 0 has to be minus 3 minus square root of 7. Very important information. Now, this is a theorem that you can prove, and I put information on how to look up that proof if you're interested in that. Otherwise, you can just take that for granted. So this is going to be very important. I'm going to be dealing, for the most part, with polynomials whose coefficients are just rational numbers. So we're going to use both of these. So in this course, and in all your calculus, and every other course you take, this is probably the case. Instead of real, it's rational coefficients. And then we can actually analyze a polynomial functions very precisely and find its zeros. It's a hard thing to find zeros. We're going to use our calculators as well to show you that in Desmos to see that. Okay, there's a corollary to this. There's a corollary to this that is very important as well. This is all in the textbook too, but I'll spell it out here. There's a corollary, something that's related to, kind of comes from, if you will. Corollary to fundamental theorem of algebra, version 2. And it's the following. A polynomial function with rational coefficients, a polynomial function with rational coefficients. So I'm not throwing any complex numbers or radicals in front of the square terms or cube terms, just simple rational numbers. But that's pretty much what we have. Now, in mathematics, yeah, we like to generalize, but in the real world, we don't really see that too often. Can be factored into a product of the linear binomial factors and something called irreducible quadratics. Product of linear binomial factors and what we call irreducible quadratics. I'll explain what an irreducible quadratic is in a minute. Quadratic factors. Now, what do we mean by irreducible quadratic? That means it's something that you might have complex numbers or radicals. I can't write it as a simple, for example, say I took do a different color. Let's take a look at some quadratics. And I'm going to look at the difference between something that is reducible and something that is not reducible. So here's a quadratic. Say it's, x squared minus x minus 12. That is reducible because I can write it as x minus 4 times x plus 3. This is an example of linear binomial factors. So this is reducible. Let's take a look at a simple one. F of x is equal to x squared plus 1. I can't write that as linear binomial factors in the normal sense. What I could write it is with complex numbers. So in this case, I get x plus I and x minus I. So we consider that irreducible. We don't write the factors like this. We can just leave them in its real form. And you could also have something like this. X minus 2, and that would factor, and I consider this to be irreducible since it would factor into x plus the square root of 2 and x minus the square root of 2. We want these linear binomial factors to also contain rational numbers. We don't want them to contain imaginary, complex, or even radicals. But they are in there. So we can use that. So irreducible in words over here, I have it in words. This is describing it. So an irreducible quadratic is a quadratic that's x squared term, quadratic that cannot be factored into two binomials with rational numbers coefficients. In this case, it's pure imaginary. In this case, they're radical. They're not rational. So that's what an irreducible quadratic is. So what does that mean to us? Okay. This gives us a lot of hints when we want to look at a polynomial function in terms of, can I find all of its zeros? Not only its real zeros, but sometimes it's imaginary or complex zeros. And not only its rational zeros, but sometimes it's radical zeros there. So sometimes those irrational zeros as well. Okay, so let's tell what the corollary actually says. So what it tells me is the following. Just kind of look at it at a high level, if you will. Say, let f be a nth degree polynomial function. So that corollary tells me that if I find all my n roots, I can write this one. Say it's x minus, x1, where x1 is a root. X minus x2, that's my second root. Times x minus x3, keep going. I might have in there a few of these irreducible quadratics. So over here, you might have this thing as, a x squared plus, or a1x squared plus bx plus c. That's an irreducible quadratic. Then you might have some more of these, or maybe that's what you have. You have those. And you have a mixture of these things, maybe some a's, this is 1, 2, 3, so a, n minus 3, x squared plus b, n minus 3, x plus c, n minus 3. If I add these three to those, and these n minus 3 of those, that would be nth degree. And I have, these, essentially, all of these, if you will, n minus 3 irreducible quadratics, meaning this would give me pairs of either conjugate radicals or conjugate complex numbers in here. But these are my real roots. x1 and x2 and x3 are the real zeros. These would be a mixture of real radicals, irrational zeros, as well as complex zeros. This looks a little abstract, but let's bring it down a tone to what you would be looking to answer on the homework. Let me give you a problem that we'll focus on in the remaining 15 minutes. So now, what do you need to do? What am I expecting you to do? And let's see how we apply this. So, for example, given f of x is a certain form, say f of x given f of x is an 8th degree polynomial function with zeros of the form, or zeros of the following. So we have, say, the square root of 5 and the square root of 2, and each of multiplicity 1. The multiplicity is how many factors you have of that. Each of multiplicity 1. So there's only one factor for each. X minus the square root of 5 and x minus the square root of 2 is a factor. Given that, and negative 4 with a multiplicity of 3, multiplicity of 3, and 2/3 with a multiplicity of 1. So this is, we're giving you part of the information. And then we're going to be asked to find the remaining. Okay, what do you want to do? First thing you want to do is find all the zeros. And then write f of x in factored form. Now, you're not going to be able to determine f of x exactly or precisely. It's off by a multiplicative constant, but at least you get the general form of it. Okay. So I'm looking for an 8th degree polynomial. So I have 8 factors. But what are they? Okay. I have 2 radicals. So over here, I can say I have 1, 2. Well, this has multiplicity 3, so that means that occurs 3 times. That's x minus a negative 4 times x minus a negative 4 times x minus a negative 4. And over here, I have another one. So let's put the roots. Let's put the actual binomial factors. So this tells me, do a different color so we can see over here. So this tells me x minus the square root of 5, that's a root. And the other one tells me x minus. I always take the negative of that, and that's one of the zeros. Square root of 2, that's a factor. Well, since minus the square root of 5 is a factor, according to the corollary, x plus the square root of 5 is also a factor. Because this tells me, my corollary tells me that radicals always come in conjugate pairs, plus and minus, plus and minus. If there's a radical, it's always in conjugate pairs. So this over here gives me x plus the square root of 2. Okay. Now this is x equal to negative 4 is a 0, so that means x subtracting a negative 4, which is equal to x plus 4 is a 0. The multiplicity is the exponent. How many times does it occur? Okay. Then I have this other one. X is 2/3 is a solution, so that's x minus 2/3 is a factor. So all of these are factors. So I can then start to write my f of x. I got this out of the way. I'm going to give a different one for you guys to try and see if you can figure that out. So what does my f of x look like? Well, f of x, it's going to be up to some arbitrary constant. I don't know. I'll call that a. I'm never going to be able to explicitly determine the function from this. I need one more piece of information. If I know one point on that function, I can pin it down. But I don't. So how might I write this? Well, I know I'm going to have over here, let's do that. It has a factor of x plus 4 cubed. Okay. It also has this factor. Now, sometimes you'll see it written this way. If we don't like to write rationals, we can absorb a constant into a, meaning I could multiply everything here by 3, and I would end up with 3x minus 2. That would have the same 0. Both of those would have the same 0. Now you can put the x minus 2/3, but just to make it look a little nicer and neater, I will put that, 3x minus 2. That is a factor of my function. And then I also have these. Yes, Colin, question.
Where did you get the 3 from?
I just picked it out to get rid of the 3 here. Notice, x minus 2/3 equal to 0 gives me the solution x is equal to 2/3. 3x minus 2 equal to 0. If I bring the 2 over, it gives me 3x equal to 2, or x is equal to 2/3. Notice both of those give me the same 0.
Right.
All I do is I saw 3 there, so I multiplied through by 3 to cancel that out. This and that give me the same 0. Then if I continue over here, I get minus the square root of 5 and plus the square root of 5. We're going to simplify this in a second. And then continuing in that fashion, I have plus and minus the square root of 2. Typically, we don't like to write them. We like to write them in irreducible quadratics, if you will. Yeah, that was just to get rid of the fractions. You don't have to. The reason I did it is just so we don't have to deal with fractions. That fraction, that 3, got absorbed into that a of our real function. It's just some of the things we do to write it kind of in a better looking fashion. Okay. x plus, excuse me, x minus the square root of 2, and x plus the square root of 2. Typically, we don't like to write these as well. So what do? We multiply these out. When I multiply that out, that gives me an irreducible quadratic of x squared plus 5. This will give me an irreducible quadratic of x squared plus 2. So what is my functional form of f of x? Well, f of x is some coefficient at the front, x plus 4 cubed, 3x minus 2. Now, if you wrote this as x minus 2/3, I'm not going to take any points off. And then x squared plus 5 times x squared plus, in this case, 2. That is a way of determining, and if I multiply that out, I could get what my polynomial looks like, with an a out in front of everything. Okay, this is something you have to practice at. Let me give you something to try now. Another problem to try on your own. And then we're done. Put it up here and then I'll give you the homework. So we're looking at polynomial function of, I'll just make this of 4th degree. And the zeros of, say, -2, 3/2 of multiplicity 1 each, and x, and also 1 minus I of multiplicity 1. And it's 4th degree. Can you give me the functional form? So while you're working on that, I will put the homework problems up here, so you'll have that at your disposal. And we'll go over these tomorrow. I'm sure this is the hard ones. The other ones are not as difficult, but we'll have the time to be able to address it tomorrow. And we'll go over that more tomorrow if you're having any difficulty. This is an example of an irreducible quadratic because it has the two roots of, -1, and this one is this one. This one, excuse me. And then it has the other root, because if this tells me they always occur in conjugate pairs, so it's 1 plus I, it's a missing root. 1, 2, 3, 4, 4th degree, I have 4 zeros. So that I'm missing, so I plug it in and then I multiply it out. So this one I could have written as x subtracting 3/2. It's always minus the root. This is x minus a -2, which becomes x plus 2. Meaning if I set each of those binomials equal to 0, I will get those values out. So if I set this equal to 0, so I set x minus 1 plus I equal to 0. I move everything over, and I get x is equal to 1 minus I. That's at 0. But since all zeros also occur in complex conjugate pairs, if 1 minus I is there, 1 plus I must be there for this particular function, because I'm assuming that it has rational coefficients. All the coefficients are rational. So given a fourth-degree polynomial function, and I'm not going to state it, but it's going to be implied that these are rational coefficients. It's not the general complex polynomial function, which you can't pin down like this. And that's why this is the one that's more useful, because most of our functions are of that form. They don't have complex numbers with i's floating around, and very rarely will they have radicals. They can. They can. Then we loosen the restriction about having the radical conjugates as solutions. So try this out. 5.3, all that is just plugging in and testing, are they zeros or not? Practice your algebra. Just understand it. 5.4 is applying the fundamental theorem of calculus. You're going to be given the degree. You're going to be given some zeros and with their multiplicity, and then you're going to be asked to piece together, this is a corollary, so you can take and write any function as a product of all its binomial factors as well as some of those irreducible quadratics. Because in the end, we like to write our polynomials all with rational, or in this case, integer coefficients. And that's what we prefer to do. Okay, any questions? And I think we are done. So I'll smile, wake up, and we will see you tomorrow, and we'll have completed in another week. Any questions? Everyone stay safe, stay healthy. I'm going to stop recording now.